Thermodynamics. Definitions of enthalpy changes. 1. Enthalpy change of formation. Energy transferred when 1 mole of compound is formed from its element under standard conditions, which are 298 K and 100 kilopascals, all reactants and products being in their standard states. 2. Enthalpy of atomization. Enthalpy change when 1 mole of gaseous atoms is formed from element in its standard state. Similar to enthalpy of sublimation, which is when a solid metal turns to gaseous atom, and same value as enthalpy of atomization. 3. Bond dissociation enthalpy. Standard molar enthalpy changes when 1 mole of covalent bond is broken into 2 gaseous atoms or free radicals. This is the same as enthalpy of atomization multiplied by 2. 4. Ionization enthalpy. First ionization energy is enthalpy change needed to remove 1 mole of electron from 1 mole of gaseous atoms to form 1 mole of gaseous ions with +1 charge. Second ionization is same sort of concept, but it's using +1 ion to form +2 ions. 5. Electron affinity. First electron affinity is enthalpy change that happen when 1 mole of gaseous atoms gain 1 mole of electrons to form 1 mole of gaseous ions with a -1 charge. This is exothermic for atoms, and this is because ion is more stable than atom, and there is an attraction between nucleus and electron. Second electron affinity is -1 charge turning to -2 charges. Second electron affinity for oxygen is endothermic because it takes energy to overcome repulsive force between negative ion and electron. 6. Enthalpy of lattice formation. Standard enthalpy changes when 1 mole of ionic crystal lattice is formed from its constituent ions in gaseous form. 7. Enthalpy of lattice dissociation. Standard enthalpy when 1 mole of ionic crystal lattice form is separated into its constituent ions in gaseous form. 8. Enthalpy of hydration. Enthalpy change when 1 mole of gaseous ions becomes aqueous ions. This always gives out energy, so it's exothermic because bonds are made between ions and water molecules. 9. Enthalpy of solution. Standard enthalpy changes when 1 mole of an ionic solid dissolves in large enough amount of water to make sure that the dissolved ions are well separated and don't interact with one another. Born-Haber cycle. Lattice enthalpy can't be determined directly. Calculate it indirectly by making use of changes for data are available and link them together in an enthalpy cycle, the Born-Haber cycle. Make sure you look like state symbols and direction of arrows. All data is given but one, so you must calculate it. Born-Haber cycle has been made using lattice enthalpy of formation. Sometimes questions will give enthalpy of lattice dissociation, which has opposite sign and arrow points in opposite direction, and this changes calculation. Down arrow is exothermic, and up arrow is endothermic. Need to form its ions using enthalpy of formation first, and last is enthalpy of lattice formation. Trends in lattice enthalpies. Strength of enthalpy of lattice formation depends on these factors. 1. Size of ions. Larger ions mean less negative enthalpies of lattice formation, as ions are larger charges become further apart, and so have weaker attractive force between them. 2. Charge on ions. Bigger charge of ions means greater attraction between ions, so stronger lattice enthalpy means it's a negative value. Lattice enthalpies become less negative down the group, like lithium chloride, then sodium chloride, then potassium chloride. Group 1 halides have lattice enthalpies of -700 to -1000. Group 2 halides have lattice enthalpies of -2000 to -3500. Group 2 oxides like magnesium oxide have lattice enthalpies of around -3000 to -4500. Perfect ionic model is when theoretical lattice enthalpies assume a perfect ionic model where ions are 100% ionic and spherical and attractions are purely electrostatic. Move toward covalent character in ionic substances when positive ion is small, positive ion has multiple charges, negative ion's large, and negative ion has multiple charges. Difference between theoretical and Born-Haber lattice enthalpies. Born-Haber lattice enthalpy, is real experimental value. When compound shows covalent character, the theoretical and Born-Haber lattice enthalpies differ. More covalent character, the bigger difference between value. Compound has some covalent character, it tends towards giant covalent. So lattice is stronger than if it was 100% ionic. So Born-Haber value would be larger than theoretical value. When negative ion becomes distorted and more covalent, we say it's polarized. Metal cation is called polarizing if it polarizes negative ion. 100% ionic means ions are spherical and theoretical, and Born-Haber lattice enthalpies will be same. Ionic with covalent character is charge cloud distorted. Theoretical and experimental Born-Haber lattice enthalpies will differ. Free energy change and entropy change. Spontaneous processes happen by themselves without external influence. Exothermic reaction forms products which are thermodynamically stable than reactants. This is what makes reactions spontaneous. Some spontaneous reactions are endothermic, and this is explained by entropy. Entropy S. Entropy is different ways atoms can share energy. If the number of ways of arranging energy is high, then the system is disordered and entropy is high. Substance that can arrange atoms in more ways and have more energy, so are more disordered, have higher entropy. Elements, simple compounds, and pure substance have lower entropy than compounds, complex compounds, and mixtures. Entropy order from highest to lowest is gas, liquid, then solids. Increased temperature of solid means entropy of it increases as the particles vibrate. Entropy increases more when boiling than melting because gases have larger entropies because they're more disordered. Predicting entropies. Increase in disorder and entropy means more positive entropy change. Balanced equation shows if entropy is positive or negative. So if increase in molecule number of product side compared to reactant side means larger entropy change, and if there's a state change from solid to liquid or liquid to gas, then entropy change increases. Calculating entropy. Can't have standard entropy of less than 0. Standard entropy per moles is seen. Entropy if kilojoules per Kelvin per mole. Elements in standard state don't have 0 entropy, and only perfect crystals at absolute 0 will have 0 entropy. Entropy is products minus reactants. Gibbs free energy change. Gibbs free energy combines entropy and enthalpy into one number. This finds if a reaction is feasible or not. So, Gibbs free energy in kilojoules per moles equals enthalpy change in kilojoules per mole minus temperature in Kelvin multiplied by entropy change in kilojoules per Kelvin per moles. For spontaneous change, Gibbs free energy is negative. Reaction that has a positive entropy but negative enthalpy will have a negative Gibbs free enthalpy value, so it's feasible. Gibbs free energy being negative means that the reaction doesn't happen or happens slowly, so doesn't happen. If reaction has high activation energy, reaction will not happen. Fine temperature reaction becomes feasible by doing enthalpy change divided by entropy change. Physical phase change are equilibria, so Gibbs free energy for this is 0. Temperature affecting feasibility. Increase in entropy, then increasing temperature will make it more likely that Gibbs free energy is negative and more likely that reaction happens. Change in temperature changes minus temperature multiplied by change in entropy. Decreasing entropy, then increasing temperature means less likely that Gibbs free energy is negative and less likely for reaction to happen. If reaction has entropy close to 0, then temperature will not influence feasibility of reaction because minus temperature multiplied by entropy will be so small and Gibbs free energy will not change much. Apply equation of a straight line, which is y equals mx plus c, to Gibbs free energy equals enthalpy minus temperature multiplied by entropy. C is enthalpy change and m is minus entropy. Positive gradient means entropy is negative, which means increase in order. When Gibbs free energy is less than 0, then reaction is spontaneous. So you see temperature that the line crosses x-axis As temperature below this, the reaction is spontaneous. Slope of line can change because product can turn to a liquid, and entropy change is different as temperature decreases. Enthalpies of solution. Use Hess's law, so when ionic lattice dissolved in water, the bonds are broken in the lattice and new bonds are formed between the metal ions and water. Ionic equation for dissolving is solid plus aqueous, forming both ions in their aqueous forms. Bonds break, and enthalpy of lattice dissociation is equal to energy needed to break up lattice, and this is endothermic, so positive. Size of lattice enthalpy depend on size and charge on ion. Smaller ion and higher its charge, the stronger lattice. Solution égale dissociation plus hydration. Instead of dissociation, they can give you formation, and all you have to do is multiply by -1. Hydration is exothermic, so negative because energy is given out to bond water to metal ions. Negative ions electrostatically attractive to delta positive hydrogen on polar water, and positive ions are electrostatically attracted to delta negative oxygen on polar water. High charge density, so smaller ions or ion with large charge means greater hydration enthalpy, as ions attract water more strongly. Enthalpy of solution is not a massive number, so hydration enthalpy is same as lattice enthalpy. Substance is more soluble if enthalpy of solution is exothermic. Insoluble substances, because lattice enthalpy is larger than hydration enthalpy and not energetically favorable to break lattice, making enthalpy of solution endothermic. Entropy needed to know solubility. Solid dissolves into ions. The entropy increases as there's more disorder because the solid changes to solution and number of particles doubles. Positive entropy causes Gibbs energy to be negative even if enthalpy solution is endothermic at high temperatures. Salt's enthalpy is exothermic because salts dissolve at all temperatures. Gibbs energy is negative, but entropy is positive, but minus temperature multiplied by change in entropy is negative. Enthalpy of salt endothermic means salt might dissolve based on minus temperature multiplied by change in entropy, which is more negative than enthalpy. And Gibbs free energy is negative, so reaction is feasible and salt dissolves.